Welcome back. This video we will be covering three subjects: latches, flip-flops, and state machines, or the introduction to state machines. This will have iClicker assignments for you to do as I progress along, although you might find one in there that I don't discuss, so be aware of that. This presentation is going to be a quick overview over these three subjects that I just mentioned, simply because you may not get to the second video, which will have additional iClicker assignments for you to do. I do this because you may not finish everything, and if you can get at least one video in, at least you got that in. So I will begin today with the latch circuit. Now, the latch circuit, which is shown on the left side, is the simplest kind of binary information storage. It's a memory unit using gates. It is very similar to the static RAM circuit that we possibly showed earlier. Let's review this. The static RAM consists of two cross-coupled inverters. One output is called Q, the other one is not Q, which is also drawn over here. They're opposite because there's an inversion between. This memory cell is accessed by a word input and a bit input going vertically on both sides, although this one is complementary. To insert data into here, we activate the word input, which opens both of these gates, and then data can flow in if we're writing or flow out if we're reading. So, for example, if Q is equal to 0, and if I then insert a 1, then that 1 will come over here and then get inverted to be a 0, and that will pop up over here. In a similar manner, a circuit that's shown on the left behaves the same but can be built in the laboratory. Now we're done with the static RAM, except to mention the static RAM is 10 to 100 times the speed of a dynamic RAM. So static RAM are used in fast cache memories. The circuitry here on the left consists of two cross-coupled NAND gates, or in the ECE book they use NOR gates. The inputs are called set and reset, or S and R. The latch state is specified by the latch outputs. Let's take a look. If Q is equal to 0, we say that the latch is reset. If Q is equal to 1, we say that the latch is set. Now there's something about these two circuits that should bother you. Notice that the outputs are identical, but they are not identical, they're the opposite, but the inputs are identical. How can this happen? Well, we'll find out. There are actually three modes of operation of the latch. In other words, to convert a present state, the present value of the latch, to another value, or the next state. Let's consider the reset mode. In the reset mode, I'm interested in making the next state of the latch equal to 0. By definition, that would be this blue variable here. Presently, it's a red 1. Therefore, we're making a change between the present state and the next state. The complementary values follow along. To do this, I make R equal to 0. That causes the output here to pop to 1. That 1 goes over here. In combination with the other 1 to a NAND gate produces a 0. So this 1 becomes a 0. So I have reset the latch. The set mode will behave as the same as the reset mode. If I take the picture and flip it, you can see that this circuit here would behave in a similar manner. In this case, to set the flip-flop, that is to make the output now a 1, I have to make S equal to 0. Now, notice the inputs are here 1, 0 and 0, 1. What happens if they're 1, 1? In this particular case, there is no way that the present state can be altered to perform anything different except repeating itself for the next state. This mode is actually the most important mode of the latch because this is the memory mode. This is where it remembers from one time to another time, from one time to another time. We call this the no change mode. Now all the possibilities, it says more possibilities, but all the possibilities are shown in this truth table. Recall that the set mode is obtained by making S equal to 0. By the way, these inputs are active low. So to do something, you make S equal to 0. That will set it. To reset it, you make R equal to 0. That will reset it. To do nothing, you make both S and R equal to 1. Now notice in this case, if the present state is a 0, the next state will be a 1. If the present state is a 1, the next state will be a 0. And then there's a fourth situation that's shown up here, which is generally not allowed because Q and not Q are both 1. Now, I kind of went over this hastily, but the table is listing S as an input, R as an input, and the present state as an input as well. And that is unusual. So the present state in combination with the inputs determines the next state. And so this is a new animal that we're looking at compared to the circuits in combinational logic where the outputs are directly affected by the inputs. Now your laboratory instructor will typically take these 4 rows and combine them into something shorter and explain the operation of the latch this way. Now I would like to explain how the latch actually works by going through this example. And we will go to the artboard with that, and then I will be giving you your first iClicker assignment. By the way, the due date for the iClicker assignment is given on the assignment, so look for that. So here's the waveform, or if it isn't exactly the same, let's check. It is the same. And what I've done here is for each value of set and reset, I have taken that truth table and I have actually written each of these 4 cases in mnemonic form over here on the top as depending upon what the values of the inputs are. So for example, if R is equal to 0, it's going to reset. If set is equal to 0, it's going to set as it shows up here. Completing this, I find out that I generate no changes as well, and then a not allowed when both R and S are equal to 1. Let me go ahead and now fill out the truth table. In the beginning, the outputs may be high or low, and so we indicate that with a hashed line. Now we're going to draw this, get a little bit of red. We're first going to reset, and then we're going to no change. And this is how you do it. When I set, then I no change. I set again, and I no change. Notice that setting and setting has no effect. It has no different effect. And so we've gotten this far. Finally, we do a reset, no change, and then a set and a not allowed. All right? So the values we get here are 0, 0, 1, 1, 1, 1. You're going to do this on the iClicker exercise, so hopefully you're going to be paying attention to me now. The opposite values are simply this. I take the waveform, I just flip it. I'm not too interested in this one, except for the last case where it actually is a 1 also. So this is the not allowed situation where Q and not Q are the same. All right, now, did you understand this? Let's go ahead and take a look at how you can do this as an assignment. Pay attention to the numbers that I've written here because you have to enter that into the iClicker assignment. Here's your assignment. Given this set of inputs that are different, I have generously given you the values of set, no change, reset up here. These are determined again by the values of S and R. Now, go ahead and fill in these values after you draw it in the waveform, And then when you have done, then continue with the lecture. Okay, let's continue. The next circuit is called the data latch with enable. I'm only going to briefly talk about this now, but much more greater detail in the next video. I would like to use this as a stepping point to the flip-flop, which is what I really want to get to right away. The data latch is simply one that is using a latch with its input of S and R being manipulated by two inputs, data and an enable. Now, if you look at this circuit here, you'll easily see that when E is equal to low, both S and R will be high. So therefore, there'll be no change here. When E is high, then the mode of operation is determined by the values of S and R. It will reset if D is equal to 0 or set if D is equal to 1. How do I know this? Well, you can draw a little chart that looks like this, and you can see very clearly pointing out that S is the complement of D. Look at up here, R is the double complement of D. All right, so S is equal to not D, R is equal to D. If D is equal to 0, then reset will be a 0. Therefore, this is the reset operation. If D is equal to 1, it is a set operation. So this is a very simple circuit. It allows me to simply, if I want Q to be high, I just set D equal to high. If I want Q, not Q to be high, then I set D to be 0, okay? Or D is maybe better to say it this way. If I want Q to be low, then D is equal to 0. All right, now we will use this in momentarily. All these diagrams I am going to explain on the next video. Again, this is my blitzkrieg technique to get through all the material as soon as I can in 1.5 hour sitting. Now, a flip-flop is basically a more advanced latch. It stores one bit of binary information under the control of data inputs, that's the same as the latch, and a clock. Well, the closest thing that we saw to a clock was this circuit here. All right, so the enable and the clock are going to function in similar manners, but it doesn't quite behave the same way. And we'll explain that in the next video. So let's take a look at how we define a flip-flop. So we have to understand that a flip-flop requires a signal that is regularly going up, down, up, down, up, down, and finally on the nth iteration, it goes up. And this is what we call the present state, beginning at t sub n. At the n plus first point, this begins another point for the next clock period. As we'll explain next time, we will calculate periods and frequencies, and I'll have iClicker exercises associated with this. This material is on the second exam, so make sure you see that one. And this is the example I will be doing and then giving you an iClicker example. Now what I want to do here is kind of go over, kind of not do that part, and just kind of talk to you a little bit about the importance of clocks. Clocks are the same thing as the rising sun and the setting sun. The up part of the clock defines the daytime, such as here in the next day, n plus 1. And this is when the flip-flops are active. They can change from a present state, which was what it had the night before, to the current one of this day. The downtime defines the nighttime, as I just said. This region is the part of the nth clock pulse, and it is not active. It is when the flip-flops are sleeping. just like when the latch is sleeping when the enable is low. The next state will be sleeping here. So the signals only change in between this point in time where the clock goes high. We'll explain this in more detail concerning my analogy for a baker on the next video. But these are the definitions I want you to get ahead, and then we're going to go right into the discussion of flip-flops, and we're going to do a little exercise with a special flip-flop called a JK flip-flop. So take a look at this. I'm going to say Q, which my flip-flop output is going to be called QN, associated with this pulse, which actually is really defined at the nighttime when the flip-flop is not active. That's its final resting point after doing activity during the day. Perhaps it's easier to see it from this point. Qn plus 1, notice that Qn changes to Qn plus 1, and then Qn plus 1 is stable here in region E. This defines the flip-flop next state. So it is when the clock is low that we, or nighttime, that we define what the values of the flip-flops were. In the present state, Qn is typically associated, if I didn't mention this yet, Qn is typically associated with the present state, and Qn plus 1 is associated with the next state. Okay, so now let's talk about flip-flops. The simplest flip-flop is, of course, one that's just like the D latch, and it's called the D flip-flop. Now, the first thing you might want to say is, why do we need a D flip-flop when I have a D latch? Well, the clocks are handled differently. It's very important to understand that, and I'll explain that on the next video, so I'm going to kind of skip over that for now. The D flip-flop loads the D input coincident with a clock pulse edge. That's part of the reason of the difference there. Subsequent changes are locked out. We'll explain this on the next time. So the input is here, the clock is here, and the present state of the flip-flop is indicating here. And this is a little symbol indicating a rising edge clock pulse causing the change. There are two active modes of operation, as I've already explained with the latch, so it's similar. If D is equal to 0, I'm going to reset the flip-flop. If D is equal to 1, I'm going to set it. And here's the truth table. Concerning the edges, I'm going to explain that on the next video, including this diagram here. I will mention that D flip-flops that you might see in the laboratory very, very soon. If not this week that you're listening to this, they often have, in addition to the D clock Q and not Q, they have an input called pre and clear, which can override the operation of the flip-flop in order to, for example, clear it initially to begin a new problem. The second flip-flop I want to introduce to you and have you do an iClicker exercise with is the JK flip-flop. In this case, the inputs are J, K, there's a clock input, a Q, and not Q. There's also a preset and a clear available. These are actually active low. There are four modes of operation. Let's not worry about the preset and clear, but associated with J and K. Now J stands for jack and K stands for kill. So you can imagine jack must make the output high and kill must make the output low, and this is what happens. First of all, if J and K are both 0, nothing happens. Notice that got around the problem with the not allowed mode with that latch. So, and that's helpful. To reset the flip-flop, I make J equal to 0, or excuse me, I make K equal to 1, and I keep J equal to 0. To set the latch, I make J equal to 1, and I keep K to 0. Then there's one more case here called toggle. If I make both of them high, then I have to define something. Well, the way it's been designed is that the output will invert itself, as it shows on this table here. All right, so if J and K, here's a plot of J and K and the next state versus the present state. If J and K are both high, it will toggle, which means that the present state of qn plus 1 will be equal to the complement of the present state. If j and k are both 0, the next state will be equal to the present state because it doesn't change, and then the other two values are reset and set. I am not going to do the timing diagram because I will address that on the next video. I am also going to, actually before I leave the JK flip-flop, let's go ahead and do an exercise that I've been promising and I almost forgot to do it. So let's flip it now to the, this is a table that you will have to understand because it will be appearing on the second exam in the following manner. Okay, this is actually question number 4 from quiz number 8. And it is just like an exam question. In this particular case, you will be given this blue chart, all right, and the red markings up here. You will not have present state and next state written, nor will you be given these. All right, so you'll have to understand how to do this. Let's fill in the next states associated with the situation of giving two inputs plus a present state. Now notice again that the next state depends upon the present state and the inputs. So this is a sequential logic circuit where the output does not depend upon the inputs by themselves, but it depends upon the prior value of the outputs, okay? Or I should say maybe the present value of the inputs determine, and the inputs, the present value of the state, the outputs, plus the inputs determine the next ones. So let's go ahead and fill these in. All right, we should do reset and set. Those are the easiest, 0 and 1. Now, no change means that 0 stays as 0. Toggle means 1 is toggled to 0. It's an inversion. All right, you got it? Any questions? Well, sorry, I can't answer them. So let's go ahead and give you an iClicker exercise. In a similar manner, what I've done is I've kept the no change set and reset set and toggle, and I've changed the values here. I want you to give me the 4 values that would appear, and just like this, the answer to an iClicker question of the left side would have been 0, 0, 1, 0 with no spaces. Go ahead and answer this question. While you're doing this, I'm going to ask a second one, so I will give you some hints on this one in case you're lost. What you do here is you fill in the reset and set, which are these values, and then you toggle this value and you no change this value. Okay, hopefully you have paused the production and the recording, and then you've answered that question. And then here's the second one for you to work out. And go ahead and try that one. I will not give you any hints on this one. Okay, very good. Now let's proceed on to the last third of this discussion, where we're going to discuss the state machine. I'm bringing this up because the laboratory will be looking at this right after our very shortly, and so I'm going to give you an introduction to state machine design, and again skip over some of the material to get to the idea of the main idea I want to get across. Now, I will be going through this very fast, and so you may be somewhat confused, but then that's all right, because then I will be re-explaining how this works and filling it in at a later time. So first of all, what is a state machine? A state machine is a sequential logic circuit whose outputs depend upon state, also known as a state machine. In this diagram, the flip-flops that we've been talking about go into this box here. They form a state. We call that the present state. The outputs that are generated are run through an output logic block, although sometimes there is no block. They form these green outputs here. To form the next state, you take the present state, you feed it back, and you combine it with an input or several inputs. And then those will then be forming what the next state will be. All right, those next states then become the present states. So let's look at our definitions here. Present state is the bit pattern of the memory elements, typically flip-flops, which are forming a register. The next state is the future state of the memory elements, and the outputs are the present output bit pattern, which depend upon the present state. Oh, and in addition, it might depend upon the inputs. Now, the example that I like to enumerate on, and I might mention it more detailed in a later presentation, is that this is a diagram of an elevator, essentially, the old-fashioned kind where you had an operator that would flip a switch up or down and go to the next floor. So let's say if I was on the 3rd floor, I would take that information of floor 3, flip the switch up. The logic would look at those two, then cause the memory elements to be the number 4, indicating I'm on the 4th floor. All right, and then should the operator turn the switch down, then from the 3rd floor, feeding that back, combining with a down switch would indicate that I should go to the 2nd floor. All right, in order to be able to see the output, and so we don't require the general population to read binary or hex, that we better have an output logic block, and that might include a 7-segment decoder and some other things, so we have a nice output. Now, we're going to relabel these, the blue, the red, and the green, as inputs X, state Y, and outputs Z. And then the present state will be indicated by saying Y sub n. The next state will be Y sub n plus 1. So you notice in this class that I have gone from the beginning of the course of A, B, C to X, Y, Z, so you know that you're now finishing up the course because there are no more letters left. And so this diagram shows you what I'm talking about. Now, I'm only showing you this as one of 3 possibilities, and I'll explain the possibilities on a later time. This is one possibility, this is a second possibility, and this is a third possibility. All right, the next thing I want to do is explain what a state diagram is and a state table, and then I will give you an example and an iClicker exercise, and we're done with this presentation. Now recall that X will be representing an input, Y will be indicating a state, and Z will indicate an output. And remember, present state is Y sub n, and Y sub n plus 1 is the next state. In this state diagram, which I'm going to show you here, and give a little extra room here, I'm going to indicate that elevator again by indicating that I'm on a floor A, which is the ground floor, and then I'm going to go to the next floor, which is called B. Now you might say, well, your elevator is going the wrong way. Well, there are some buildings that actually go down instead of up, and it's more convenient for me to draw things going down than going up. For example, I believe the Pentagon has 6 or 7 floors that go below. So you can either interpret that or just look at the picture upside down. Now, the diagram shows 2 arrows. These arrows are indicating action caused by inputs X1 and X2. X2 is the input, and in addition to that, I have a demarcation mark of a slash sign and indicating outputs Z1 and Z2. Remember the colors. Red is indicating a present state or the next state. Blue is indicating an input, and green is indicating a output. Now, in this particular case, X2 is, if I get X2, I'm going to go from state A to state B, or from the ground floor to the first floor. If I get input X1, then I'm going to remain in state A. While I'm doing this, I will output Z1 in the first case and Z2 in the second case. Okay, the dividing sign has nothing to do with division is just separating these two quantities. Now in the ECE book, you will find them just written with the inputs, and the outputs will be, instead of a slash over here, will be written below the states here and here. My next video, at a later time, another time, I will go through a ECE book demonstration of how to interpret those results and do some exercises on your ECE book concerning state machines. So these are something I call bubbles. So we label the bubbles ABC, etc., etc. And then we'll find out at a later time that these arrows, if they are labeled like this, are called mealy design. And if they just have the X like this, then without the Z, or if the Z is located below the state, we'll find out later. Those are called Moore machines. So mealy machine and Moore machine. Now, associated with the state diagram is a state table. I've repeated the state diagram here, and I want you to see that for these two states, A and B, showing only the arrows associated with A, which there are two. Each of those two arrows are represented by these two rows. So the first row indicates that I have a present state of A and an input of X1, and I go to state A and I output Z1. This arrow, going vertically down, is showing that the present state is A and the input is X2. Now I will go to state B and output Z2, or advance to state B. I do not show any arrows associated with B for simplicity, but there should be, and this example is a much more comprehensive example. And this is the example I would like to then go through and show you how to fill in these six values, and then I'm going to have you fill in the remainder. Okay, so here it goes. This is on quiz number 9, problem number 3, actually. So here I have 3 states, and I have 6 arrows, so therefore I have a state table with six rows. So let's consider what happens here. In the particular, I would like to fill in the first 3 rows, and I'm going to give you as an assignment to do the last 3 rows. Now, let's just go ahead and take a look at the first case. If A has an input of 0, it is going to go to C and output a 1. Now, I've indicated where these are going to be located. All right? So A with a 0 means that 0 is located here, as shown by the dashed blue line. A going to C would be something I would write under next state. So let's go ahead and do that. I've got to do it like this. Okay, I'm lucky that I had C or red already picked out. And then the green 1 then is placed over here. So let's go ahead and do that and put the green 1 here. All right, that's how I fill out the first row. That's associated with this path here, okay? Now let's do the next path. Starting from state A, the input is 1. This 1 is this path. So therefore, A with a 1 goes to B, outputs a 0. Outputting a 0 going to B. All right. The next thing I'm going to do is fill out the case for when I have a B and input of 0. Here's B with an input of 0. All right. So B with a 0 goes to C, outputs a 0. All right. So hopefully you understood how I did that. This is a question that often appears on the second exam. Now, let's go ahead and have you complete it now. So we'll turn on the exercise here. So in this box, I would like you to fill out these values. They will be letters on the left side and numbers on the right side, in other words, 0 and 1. And please fill it out in the following manner. Like start off with the one on the left on the upper, then go to the right, and then follow the zigzag path. Okay, follow that path and fill it out. Okay, that is the last iClicker assignment that I'm giving to you on this lecture. Proceed on now on to the next video where I'll have additional assignments, additional discussion of the material that I've discussed, plus additional iClicker assignments for you to complete.